Hey, what's up, guys? This is Cheng here. So today, LeetCode number 1044, longest duplicate substring. Okay, so you're given like a string S, right? And then you need to consider all the duplicated substrings, right? So substrings is a string that occurs 2 or more times, and the occurrences may overlap, right? And then return any duplicated substrings that has the longest possible length. Okay, if the S does not have a duplicate substring, then return empty. Right, so basically we need to find the longest duplicate substring. For example, we have banana, right? So the longest one is ANA because we have BANANA, right? So we have ANA here and we have ANA here. That's why it says, the duplicated string can be overlapped, right? This one and this one, right? That's why it's overlapped. Okay, and so for example, A, B, C, D, right? So this one doesn't have any duplicated string. That's why the answer is the output is empty. Okay, and then we have constraints to maybe 10 to the power of 5, and then S is only consists of lower English letters, right? So I mean, at the beginning, I was thinking about, at the beginning, I was thinking, is there like DP concept here? Then I try to define like state, right? Basically, if we have a DP, I and J, right, to represent the range of the of the string from I to J. If the longest between this range is equals to a certain number here, I mean, can we have like a state transition function? Then yeah, I try to think it in this way, but I couldn't figure out like a state transition because usually when we have like a string DP problem, we most of the time we can just use like the I minus one, right, and then and J or or like uh or like I J minus one, right, to get the state transition function here. But for this one, it's different, right? Totally different because here we're trying to get the duplicated string, right? There's no way we can verify if the previously state has any duplicate string with the current one. So basically, I couldn't figure out any state transition function here. That's why I just simply stopped on that DP root there. Then like I was like, maybe I just should. Then it's always, if you couldn't find see like a solution right away, always try to solve it with brute force first, right? So what is the brute force way to solve this problem? Obviously, the brute force way is that we can simply try all the possible length of substring, right? Because it's obviously we can try 0. I mean, if the length is 0, of course it's empty. Or we can try length of 1 or 2, 3 until n, right? Basically, if we know so if we're trying the length of 3 substring, then we can simply use a sliding window, right? So what I mean is like this. So if we know we know a length for substring we're trying to check here, we can simply use a sliding window, right? I mean, basically we just do a sliding window of size of 3, and then we move it here to here, right? And then we move to here. Basically, every time we have a new string here, right, we can simply store that string into a hash table or set, right? And then later on, when we find a duplicate, when the current string is already exists in the hash set, and then we know, okay, we find a string, a duplicate string with this length 3, right? And then we simply just try everything from 0. 0 we don't have to try, okay? It's from 0 to 1 to 2 to 3 all the way until n, because the longest we can get is n. Actually, it's not n, right? Because it should be n minus 1. because n is like n is will not we will never get like a duplicate string with the same length of this. It has to be at least at most n minus one, right? So that's the brutal first way, right? But that has a like I think it will TLE because remember we have like a 3 to the times 3 times 5, 10 to the power of 4. That's the constraint, right? You know, uh, storing and checking the existence from a set is O of 1, right? But you know, like you said, we will basically will try all the length. That this is O of n, right? And within the within each of the length here, in order for us to get the current string, right? Basically, we have like current string, current s, right? And then we'll add the current one. We'll basically we'll appending the string to the end is O of 1, right? But meanwhile, we also need to remove a string from the beginning, right? Let's say we have A, C, B, D, A, right? So we have like A, C, B, D, right? So let's say that at the length is 3 here, you know, when we are like at here, we have A, C, B, D. But at this time, we need to remove A at the beginning so that we can get the current string, right? So removing this one, it's going to be a O of n time complexity, right? So even if we don't remove it, do a slice of the string, will also cause us O of n. So that's why if you do it naively with this kind of string set, it's going to be a O of n squared time complexity, right? I think that will basically TLE. Okay, and yeah, let me think. Yeah, actually, it's going to be a O of n cubed because you know to try each of this one, we have O of n, right? Now we have O of n here, and for each of the length, you know, we will be scanning all through everything. We're gonna scan through this entire string here, right? To scan it through the entire string, we have another n, right? And like I said, you know, to get the current string, you know, either we remove the first one or we do a slice of from with like a range here. There's gonna be another n, right? That's why it's going to be n squared times this n. It's going to be n cubed time complexity. That will definitely TLE. So that's why, you know, we have to somehow improve that, right? So there are two things we need to do here in order to make this algorithm from n cubed into a n log n. So the first one is this. So first one is this. Do we really need to try everything from 0 to n minus 1? You know, probably not, because this one is actually it has a very obvious trending here. It means that, you know, the longer basically basically if given like a k here, if the k size string substring does not have any duplicate, right? And it means that, you know, k and k plus 1 and then until n minus 1. So this part will never, it won't have any duplicate string. So the possible duplicate string size can only be on the left side, which is starting from 0 to k minus 1. Right? Same thing for the other side. Let's say given like a k, right? Given like a k, if the k we find like size k size k duplicate substring, then it means that, you know, from 0 to k, right? It's all possible. We can always find that. You know, for example, we have banana, B-A-N-A-N-A, right? So this answer is it's k, it's 3, right? K is equal to 3. Then it means that from 0 to k, we can definitely find a substring with this size that can be duplicated. Obviously, you know, 2 is possible. 2 is NA and NA, right? There's duplicate. And then for A, of course, AAA, right? For empty, yeah, right. That's why, you know, as you guys can see, now we have a binary search improvement here. Basically, we can binary search this length of a substring. That can at least knock out this n and to replace it with a log n, right? So that's the first thing. But still, right, even though we have knocked out this one, but we still have like an n square for each of the length. This is where we also need to make some changes. Otherwise, you know, n square log n will also TLE, right? And how can we efficiently remember, right, to store all the previously visited the substring into a set? Okay, I think some of you must have already heard about it, this rolling hash, right? Because, you know, so where did we spend this n here? You know, obviously the first n is not, it's like unavoidable, right? Because we have to scan through the entire string, but and it's the second n that we can do something about it, right? Because like the second n, where does the second n comes from? Basically, it comes from the string manipulation, right? If we can remove that somehow, then that'll be great. And so then that's when we need to use a rolling hash, you know. So rolling hash means that, you know, every time when we reach a new string, right, we can use O of 1 time to get the new hashing values for the current string, right? So that we don't have to spend O of n time to get the a new string. And to do that, there's like, I think what is called Rabin Karp. I think it's called Rabin Karp solution algorithm, right? So we can use that. So what does that do is like this, you know. How should I explain this? Okay, so if you try to understand, to be able to understand the Rabin Karp algorithm, you know, I think it's best if we use like a 10 based integer. Okay, 4, 2, 1. Okay, let's say we have this kind of k is equal to 5. Sorry, this is 6, right? This is 6. So if we have like a sliding window of the of a size k, and they are like 10 base integers, and let's say we have 3 here. Okay, so how can we quickly find if we have sliding window, how can we quickly find the values for this kind of you can call it string or integers? Obviously, you know, in order to get the values for this kind of thing, you know, every time we start from the first one, right? So the first one is like what? We have two we have a rolling hash, right? So actually the hash in this case is just the value of this integer. Okay, that's the rolling hash we're trying to calculate here. If, for example, if this like 10 base here, right? So the first one is what? We have a rolling hash. We call it h, right? H is going to be um, at the beginning, h will be 0, right? So at the first time we have 2 here, so it's going to be h going to be h times 10, right? Remember we are like 10 base, and then we plus 2, right? And the second time we have this one, h is going to be h times 10 again, right? And then we do a plus 4. So what do we have here? H in this case is going to be 2, right? And now when we're at here, obviously this is 24, right? That's how we get 24 in here, okay? And then we do it again, right? So this thing is going to be this one plus what? It's 5, right? So this is 2, 4, 5, right? So this is very easy to understand because this the 24 is actually the 24, right? The 245 is the 245, so on and so forth, right? This one is going to be a plus 4 again, right? Then we have 2,454, right? So in the end, we have, so at here, we have this kind of values, right? Now, let's say we are trying to move like one more, right? Trying to include this 3 here. Okay. Obviously, now the new value is what? The new value is this. It's 454,213, right? And how can we get the value of 454213 from here, right? Obviously, what we can do is like this, right? So we have h gonna be the what? So first, we use the same formula here. So we get this one. We got h times h times 10 plus 3, right? Then we get this number, right? We got 2454213. Okay, and then how can we get this part? Simple, right? We simply subtract the first digit, right? Which is what? We subtract 2 times 10 to the power of 6, right? So if we subtract this one, then we have 454213, right? I'm just using this kind of 10-based examples to explain the rolling hash algorithm, right? So because this one is the most straightforward one, and actually that is the exact same algorithm we're going to use. The only difference is that instead of 10, it's going to be 26. Basically, in our algorithm, it's going to be a 26 base because we have, instead of the digits from 0 to 9, we have the letters from A to Z, right? That's why we're going to times 26, and the remaining are exactly the same, right? So we have 26, and here we're going to convert this number. We're going to map this one, right? Map this integer, the letters to integer from 0 to 25, right? This part, and then that's the the what is it called? Rabin carp, yeah, or whatever it's called. Okay, and we can start coding then, I think, right? But there's some also some improvements that we need to do during the coding. But let me try to write the main logic first. We have n is going to be the length s, right? So L is going to be the starting from 0, and the right boundary is going to be n minus 1, right? Or you can put n because we're doing a binary search, so either n or n minus 1 should work. And since we're going to work on the integer numbers instead of the strings here, to make it easy, I'm going to make like numbers to convert that letter into its corresponding integer value, kind of a minus word, right? A for C and S, right? And then the binary search template. So we have L is going to be hard, so middle, right? It's going to be the L plus L minus L divided by 2. And then we have helper function, right? Basically, if the helper, the middle, right? We're trying to get the maximum, the longest, right? So which means that, if it's a maximum, we are going to assign the middle. If helper functions exist, it means that we're going to have to a left equals to middle, because I think I've already talked about this several times. If every time we are getting the maximum values in the binary search, we're always going to do this L equals to middle, because in this case, we're looking for the right half, okay? And the L might be the answer. That's why we do a L, right? It's basically we're trying to move the cursor to the right, as to the right as possible. Okay. Else r is going to be the middle -1. Okay. And remember, every time we do a l equals to middle, we have to do a +1 here, right? That's what. Otherwise, if we have l is equal to 3, r is going to equals to 4. In this case, if we don't do a +1, the middle will be stuck as 3 forever. That's why we have to do a +1 here. Okay. So that's that, and then we simply return the. Oh, and here I think instead of the length, we're returning the actual string, right? So which means in this helper functions, actually we need to, instead of, besides true or false, we should return the index, basically either the start or the end index of this duplicate string, right? And yeah, so now let's implement helper function, right? So we have that's going to be the length, right? So I use uppercase L represents the length of the substring, duplicate substring we're trying to check here. Okay, and then we have scene, this is going to be the set, right? So we have a current hash, right? So I call the current hash, it's going to, as beginning it's going to be 0. I mean, there are like a bunch of ways you can check this one. So for me, I get the hash, I get the base hash, right? First is going to be this L in L. Basic current hash going to be what is that? Current hash. Okay, current hash, right? Times 26, and then plus the nums of I, right? So that's how we get the current hash to the place where before we need to subtract the value from the hash. Okay. Then so we're gonna make some like improvements here, because keep in mind that this one will be if we just do this one, it's gonna be an issue because the length is just too big. Can you imagine that? If we have a 10,000 length here, if we do this kind of like 10,000 times, can you remember how many digits we'll have in the current hash? Right, it's gonna be a 10,000. I don't know. So it's gonna be like 10,000 digits, right? That's crazy. It will definitely overflow even in Python, right? So, but I'm trying to outline the main logic here. So here we have right. So that's gonna be the starting point, and then for the I in range of so for me I do this. So L to N, basically. Now the L is the one from here. Let's say we have this one, right? Let's say the L is equal to 3. Right, so now the I is pointing to here. So this is the first place we need to basically subtract something from this hash value, right? Basically, the current hash is going to be again. So the first still is still this part, but the only difference that this one we need to subtract, right? The nums of I minus L, right? And then we do a times. Now remember it's 26, and then to the power of L, right? So that's the thing we need to subtract. Remember, it's a 26 base instead of 10 base, right? And yeah, so basically, if the current hash, right, exists in the scene, right, and then we know, okay, we have find a duplicate string with this current length here, and then we can simply return the start index, right? It's going to be I minus middle, right? +1. That's going to be the start index for this one. And then we also add the scene dot add into the current hash, right? So otherwise, if nothing happens, we simply return -1. So -1 means that we didn't find a thing. We didn't find like a valid duplicate string here. So mm, for if that's the case, here we have to let me see. So we have an answer going to be 0. Okay, so here let me see. Yeah, so we have to make some change here. So instead of check the result directly, I save it into a variable here. Basically, if this one is either star or greater than 0, okay. Then besides this one, we also gonna assign this start to the answer, right? Because the start could be -1, right? So that's why we have this. And then in the end, we simply return the answer dot answer plus left, right? So that's how we get the original string here. Because in the end, the L, either the L or R is a string. It basically is the length of the duplicate string, right? It's the biggest, it's the longest length, and this answer will be the starting point of that string, and that's why we can just use this expression, to get the original string. All right, cool. I mean, that's the basic idea here, but if you run it in this way, like I said, this thing, I think it will TLE or something. Let me try it. I think this one will work, right? Banana? Yeah, I think banana, at least it'll work because this one is not that long. But if you try to submit with this one, I think it will TLE. Yeah, because this hash is too big, right? And if you just do this, and I think the computer will, I mean, will go crazy. So, and also, this is also another part, 26, do a 26 power 26 of, let's say 26 of what I'm trying to do here, of one of 10,000. If you're just trying to calculate this one blindly, it's because remember the L could be pretty big. This one would take a lot of time, and as you guys, not a lot of time, but some time. But as you guys can see, so for in each for loop here, we're calculating it here. So the first thing we can do is that we can just extract this part into a constant, so that at least we can remove this duplicate calculation. I can just do this, right? Now I can do this. But if I run it again, I believe it'll still TLE. This is because, like I said, because the hash value is too, man, it passed. Well, I wasn't expecting that this one will pass. Okay. Okay, let's just pretend it didn't pass, okay? Because as you guys can see, this one is it's pretty slow, right? This is because, this one is too big, that's why we have to somehow do a modular with this current hash so that it won't overflow. Because in Python, it passes because we are lucky to use Python. Because in Python, it will not throw an overflow exception, right? And it will somehow do some internal conversions to make sure it will not overflow. But that's, as you guys can see, but that's why it's pretty slow, right? So the ideal solution is that we have to do a modular of this one, right? At the beginning, I was choosing something like this. This one's pretty big number, right? And basically, every time when we have like this one, have a hash, we do a modular to make sure it will not overflow, right? And this one is also so here is also like modular, right? Okay. And also for this one, this one actually is the we have this one. If you do something like this, it will still work, right? But like I said, even this part in Python, even though it will not overflow, but this one will become pretty big, right? So this is not the correct way of doing a modular, because we should, every time when we do this, basically, as long as this one we have, every time when we have like L here times L, we should do a modular, basically, for L times, right? Ideally, we should have like a while for loop here. Every time we multiply L, we should do a modular. But in Python, we can simply use a power built-in function, right? 26 L and then mod. Basically, this power function will do that for us. Okay, and yeah, as you guys can see now, at least the current hash, the hashing value will not overflow. Okay, so if we run this one, okay, let's submit. Yeah, see, as you guys can see, this one it failed at this testing case. Why is that? Because of the hashing collision, which means that this mod number is not big enough. Because we could have like many combinations of the hashings here. If we didn't choose this mod number carefully enough, we might end up with a hashing collision, right? That's why this one failed, because it's thinking that this one, this ym something, have, if we use this kind of formula here, it end up with the same hashing result as a previous string, for some reason. That's why it failed. Then to solve this one, we have two options. I think the first one is that obviously we can increase this, right? I think we can increase this one to a big number. I don't know, maybe 60. I don't know if this will work or not. Let's see. Yeah, and this one, it's also failed. See, for some reason, because I think it's also because of the collision, and this is because when you choose like a mod function, try not to use like the ones with a lot of zeros, right? Because this one will end up like will basically will greatly reduce the unique hashing values we can get. That's why when we have like a modular, remember, a lot of functions we use 10 to the power of 9, right? And we do a plus 7, right? Instead of 10 to the power of 9. That's why that's the one way of preventing the hashing collision. So we can do this one, I guess, either -1 or +1. Let's see if this one works. Yeah, see. So this one worked. I think +1 should also work. Let's see. Yeah, also works. So we simply just make this like a number, like a random number, instead of having a lot of zeros in the end, right? So that's one way we can fix it. No, but if this one, let's say for example, if this one will overflow in some of the languages, either Java or C#, which means we cannot have like this big numbers. So what we can do, basically, when a common way to solve a hashing collision is, instead of having one hashing function, we will have two. Right? Basically, we'll use two hashing functions to, what actually? Let me try this one first. Let me see if this one works. Okay, yeah. Okay, I just want to make sure. I just want to make sure this one still fails. Okay, so basically, continue back to what I was talking. So instead of one hashing functions, we will have two hashing functions, right? So in that way, the combinations of the hashing result will be much more, right? That's why if for that one, we can use two hashing functions for the same range of numbers to avoid the hashing collision. So what do I mean by that is that instead of then first two hashing functions, we simply just need two a mod, right? So we can have mod2. So for this one, I can simply do a 32 minus 1, right? I can just do this one. And then I'll just have two hashing values here. Here I'll have like 2, right? This 2. And then, okay, and when we insert into the set, basically we'll be combining those two hashing values into one, right? Which means we're going to have like a tuple here. Okay, that's that. Oh, and we also need like another A here, right? Because we are also doing like hashing, like the modular here. It's going to be a mod2. So here is the same thing, hash2, right? Hash2, and here's going to be A2, right? And now same thing, we have to check the tuple instead of the single hash, right? And then here, add. Okay. So, yep, I think that's the thing. That's it. So if I run the code and submit, did it? Oh, here, mod2, right? Oh, here. That's the downside to do a copy paste. It's very likely you will forget something. Cool, right? So this one also works, right? So now, as you guys can see, instead of increasing using a fairly big numbers, we can also solve hashing collision by introducing a second hashing function here, and then use both of the hashing result as the key. And yep, so as you guys can see now, the time complexity is what? So we have log n here, right? Log n, and here in the helper functions, this is n, right? And this is also n. That's why it's going to be n log n. And cool. Yeah, I think that's it, right? For this problem, and I'll stop here. And thank you for watching this video, guys, and stay tuned. See you guys soon. Bye bye.